Ductility. Ductility of an element shows its capacity to deform in the inelastic range without collapse. For example, in the concrete members, reinforcement is present, and in the reinforcement there is yield. There are two main portions: yield region or elastic region and inelastic region. Okay, so after yielding, there is so much release of energy. That is called inelastic range, and after the in the inelastic range, it doesn't mean it is going to fail. Okay, it have the reserve capacity before the final failure, that is in the inelastic range. Ductility of an element shows its capacity to deform in the inelastic range without collapse. Okay, what will happen, this inelastic range will give us time or warning before failure, so that is called ductility. Due to these inelastic deformations, the energy is dissipated, making the structure relatively stable against the earthquake forces. Okay, so ductility, what will do, the energy dissipation will occur and making the stability of the structure. If these deformations successfully occur in the two opposite directions, causing reversal of stresses in the members, hysteresis loops are produced, dissipating energy in each cycle of loading, unloading, and loading in the opposite direction. For example, here assume, uh, let me take the pen. Okay, here is column. Okay, when first it will deform in this direction, then after coming back in this direction, then so much energy will be used in this phenomena. Okay, first column will go in this direction, then come back into this direction. This in that process, lot of energy will be utilized. Okay, so this hysteresis loop is the measure of the energy. Okay, measure of energy loss is called hysteresis loop. So there will be lot of energy loss due to this movement. Okay, due to this reversal of stresses. Response modification factor. The response modification factor of structure is the ratio of the seismic base shear of an elastic system to reduce base shear depending upon ductility. Response modification factor is a very important factor. For example, if you have a base shear 800 kilonewton, okay, base shear means seismic force, horizontal force acting to the structure. uh, if you have a base shear value of 800 kilonewton, so seismic base shear is a factor which will reduce the base shear. Okay, depending upon what? Depending upon ductility, energy absorbing capacity of your structure, increase in natural time period due to yielding, and increase in damping ratio of the structure. So depending upon these factors, the response modification factor works. Okay, the actual base shear is 800, but due to response modification, that base shear can be reduced to 200 kilonewton. So that is a very important response modification factor. If shear wall, these are the nomenclature. If shear wall or brace frame, okay, provide support to gravity loads and all the lateral loads, the structural system is a bearing wall system. In other words, gravity loads are resting on walls, that is bearing wall system. If separate systems are provided to resist lateral and gravity, okay, gravity loads, the structural system is called building frame system. Okay, the means frame members act separately, so that is called building frame system. Special moment resisting frame are frames specially detailed to provide high ductility and support for lateral and gravity loads by flexural action. Flexural action means moment shear action. Okay, what is special moment resisting frame? For example, when we design simple beam, simple column, okay, the rest of the procedure in all the designing of members is same. The difference between the ordinary design and special moment resisting frame design is that of detailing. We detail the members. Details mean a sketch of reinforcement of number of bars, spacing of stirrups. So that is called detailing. Okay, so we detail in such a way that there will be lot of ductility. lot of energy dissipation. So we detail in such a way, then that type of member is called special moment resisting frame. Resisting frame with masonry shear walls are called MRWF system. That is the abbreviation. Dual system are those in which more than one system are used together. Maybe special moment resisting frame with bearing wall system. Okay, a dual system can also be used. Here is the response modification factor. Okay, BWS bearing wall system with concrete or masonry shear walls, response modification factor is R 4.5 and the height limit is 49 meter. Similarly here steel or concrete special moment resisting frame 8.5. Okay, height limit is none. Similarly masonry, okay, concrete shear wall with special moment resisting frame 8.5, height none. Okay, let me show. Okay, okay, here in the slides I have shown a short table. Okay, in the core JBC 97 you can see the whole or large table depending upon the structure type. Okay, structure system. It is response modification factor, our strength factor. I will also discuss how to use. You can see details by yourself, but right now I am discussing response modification factor. For example, in the table, slide table, ordinary brace frame is not discussed, ordinary concrete, okay, also not discussed. Okay, here is the moment resisting frame. If special moment resisting frame, concrete 8.5. Okay, concrete with special shear walls, concrete with special moment resisting frame 8.5. Okay, so this is a large table. Okay, you can come here, and depending upon your structure type you can select the response modification factor values. Next is the value of the response modification factor is determined from the consideration of structure's overstrength capacity beyond the point at which the elastic response of the structure exceeded. Means the all the or the major part of the response modification factor is depend upon the strength or overstrength limit beyond the elastic range. Means in the inelastic range, that is more dependent upon the response modification factor. The value of R always exceeds unity, which indicates that all structures are designed for forces less than would be produced in a completely elastic structure. What it means, I already given an example. If there is a 800 kilonewton base shear, then the response modification factor can reduce. Okay, for example, if it reduced to 200, it means 800 divided by 2, then it is reducing to uh, 800 divided by 4, that's why it is reducing to 200 kilonewton. So the response modification factor value is greater than 1. So what it means here, after dividing, then we are going to design the member against less base shear. Okay, why less? Because by dividing R the value will be less. This reduced force level is made possible by the energy dissipation and dissipation capacity of the structure at displacements in excess of initial yield. After yielding, there is lot of deformations. Okay, so this deformation will cover energy absorption and energy dissipation. Okay, so these all will cover the response modification factor. Okay, so response modification factor will cover all these things: energy dissipation, energy absorption. Okay, after the yield. Seismic importance factor. The factor is equal to 1.25 for essential and hazardous facilities and 1 for special occupancy, standard occupancy and miscellaneous structures. What it means, for example, if you are designing a hospital building, then you definitely go for a high importance factor 1.25. For nuclear reactor, for important buildings, you can use importance factor 1.25. By using 1.25, it means you are designing the members against 25% more forces or using a higher factor of safety. Again, that is a very small range. Okay, for detail, again, You can go in the table. Okay, here occupancy category, you have to select your occupancy, like what type of your building is. For example, building house group. Okay, all structures with occupancy greater than 5,000 persons. One, okay, is essential facilities, fire and police stations, garages and shelters for emergency vehicles. Okay, aviation control towers. Okay, so all important type of structures you can use the seismic importance factor 1.25. Its maximum value is 1.25, minimum value is 1. Seismic response coefficient. The seismic response coefficient is the fraction of the total dead load of the structure that is acting as a base shear on the structure. Let me explain. You are designing a building, then definitely that building have some weight. Okay, so what is seismic response coefficient? Seismic response coefficient, that it will take the total load of this total load of the structure and multiply with, for example, 20%, 10%, and take that load, take that value and apply as a horizontal load. That is called base shear. Okay, so let me read that definition. The seismic response coefficient is the fraction of that total dead load of the structure that is acting as a base shear on the load. Okay, we calculate the total weight of the building. Okay, when we go definitely for the example, then we will also see in the detail the seismic response coefficient. So seismic response coefficient is the fraction of the total weight of the building which is acting as a base shear on the structure. Okay, this means that the cs will be, cs is the base shear will be cs into w. We multiply the total weight of the building with the seismic response coefficient, that will become the base shear. This seismic response coefficient depends upon, this factor depends upon velocity acceleration based on ground response coefficient, CV or CA, importance factor, response modification factor, and time period. Okay, so this seismic response coefficient depends on all these things. Here is the value of seismic response coefficient. Cs is equal to Cv I over RT. Cv is velocity based coefficient, I importance factor, R response modification factor, T is the time period of the building which is you are going to design. If time period is greater than Ts, subjected to maximum and minimum values. Okay, if your time period value is greater than Ts, then you have to must check for maximum and minimum values. How to calculate the Ts? Ts again Cs over Cv over 2.5 Ca. These values Cv and Ca you can pick from the previous slides or from the book. That depending upon the seismic zone and soil type, you can select Cv and Ca. Okay, again Ta will be after calculating the Ts 0.2 of Ts. Okay, where Ta will be used here. Okay, now the maximum mini values. Maximum value 2.5 CAI over R. Okay, controls when T value, your time period is in between TA to TS. Minimum value is 0.11 CAI or 0.8 ZNVI over R for zone 4. So here is the seismic response coefficient value. You have to check against the maximum and minimum values. Okay. Seismic dead load. Okay, what loads will be considered in the seismic dead load? In software language or in the design of buildings in the softwares, this seismic dead load is named with mass source. Okay, there is another name that is mass source, but the purpose is the same. So now I'm discussing the seismic dead load. The seismic dead load consists of the following. Okay, dead load of the structure means beams, columns, slabs, all type of dead load of the structure that will include in the seismic dead load. Second, 25% of the floor live load for storage and warehouses, where you are going to store your bags of food, wheat. okay, rice, etc. And warehouses, you have to consider 25% of the live load. And third, a minimum allowance of 50 kg per meter square for movable partitions. Okay, you have may have seen that in the office buildings there are partition walls, lot of partition walls. For the a minimum allowance of 50 kg per meter square for movable partitions will be considered. The fourth one, the total weight of the permanent equipment and fittings. For example, on any floor you are going to install a machinery, then that machinery will also, the load will also come in the seismic dead load. Okay, in the seismic dead load, these four things will come. Okay. Now, here is a magnitude of base shear, UBC refined formula. Base shear can be calculated as CS into W, that is already discussed. Maximum inelastic displacement calculation formula is 0.7 response modification factor and into delta S, where delta S is the displacement corresponding to the shear given above. Okay, when we apply this base shear to the building, then definitely due to the horizontal base shear there will be deformation, and the deformation will be delta S. UBC simplified formula. Okay, this is the approximate method of UBC. In the detail method I will discuss later. First, this is the UBC approximate method. That is, the base shear will be can be calculated. V is equal to 3 into Ca over R into total seismic wave. Okay, this is conservative formula having the following restrictions: ordinary occupancy type, light frame construction not exceeding 3 stories, and any construction except bearing wall system but not exceeding 2 stories. So these are the limitation of UBC simplified. This is just giving the brief idea about the UBC simplified formula, but definitely we will go for the detailed method. When an earthquake hit to the structure or the building, then definitely the earthquake force or energy transfer from the base of the building to the top of the building means forces will be transferred from the base, first story, second story, third, and gone on the top story. So for that distribution or detailed distribution, here is the formula. For uniform distribution of mass over height and first linear fundamental mode of time period, the distribution of base shear may be simplified as follows. That is the formula. V1 is the base shear calculated depending upon the formula. V is equal to CSW. And for base shear for any story, weight of that story, height of the that story, and total cumulative sum of weight and height of all stories. Okay, hi, height above the base to the level. Okay, height above the base to the level x. Okay, definitely these terminologies will be cleared in the example. In order to account for higher mode effects in the above expression for long periods buildings, an additional force Ft added at top of the structure. In the free vibration analysis, I have discussed that when we push the mass moved in the horizontal, then it will come back to its original position. After some time, it will stop. The first cycle of that building or mass or any structure, that is called fundamental time period. And for other higher modes or other modes, when after some time the building will stop vibrating. Okay, the next modes. Okay, this formula is for the first mode, first linear mode of fundamental period. For other modes to count, okay, there is an additional Ft force added at top of the structure. Here is Ft, the value of Ft will be 0.07 multiplied by time period of the building multiplied by base shear. When time period is greater than 0.7 seconds, then you need to consider the value of Ft. Okay, Ft, then formula will be Ft plus mission Fx. The base shear will be remain same, but the Ft will be added. In such cases, V minus Ft multiplied by Wx into Hx divided by Wi into Hi. The detailed discussion about this formula will be cleared in the example. Okay, here the additional force will be distributed in the stories, especially in the above story, above top story.